Good afternoon. My name is Christian Seltzer. I'm the founder and president of the Convergence Initiative. And today is my pleasure to introduce our speaker for the Convergence Sci-Art Side talk. The Convergence Initiative, in partnership with the Faculty of Fine Arts of Concordia University, is pleased to introduce biomimicry, a creative technique in design education delivered by Professor Erwin Regler. Erwin is a Montreal-based artist of German origin. He studied at the University of the Arts in Berlin and at the State University of New York at Stony Brook. Apart from his practice in sculpture, Erwin teaches courses in biomimicry, computer-assisted design, and digital sculpture at Concordia University. Today, he will talk about biomimicry and the attempts to solve human problems by emulating organisms, processes, and systems observed in nature. So I'm really happy to introduce him for our talk today, and please let's welcome Erwin.
Biomimicry, which goes back about half a century. I want to explain current movements in biomimicry. Most importantly, I want to explain how we conduct projects in biomimicry here at Concordia University in the Department of Design, because this is where myself and a colleague of mine are teaching biomimicry here. As to the historical background, most of biomimicry, well, practically all of it is case-based reasoning. Case-based reasoning is also called analogical thinking, and this is a method that humans tend to use in order to understand an unknown phenomenon. In order to understand something that we do not know, we make a comparison and we compare it with something that we know. And this is a very common practice. For example, a car mechanic will the car mechanic can essentially run a diagnostic on the car and then find exactly what is the problem of the car. But most of the time, the mechanic will not do that. Most of the time, they will just look at the symptoms that the car exhibits and then compare it to a car that they had to fix in the past. So that's the analogy. A very simple analogy would be an indigenous people living in the prairies 300 years ago will for the first time see a locomotive and he will compare it to a horse, call it the iron horse. So biomimicry is a method that creates this kind of analogy between a living organism and a human-made system or artifacts. And the fact that this is a case-based kind of reasoning is kind of important for the procedure and in order to understand it. It's no surprise that an all-round artist like Leonardo da Vinci looks at nature first, looks at birds first, when he attempted to invent a machine for flight. Studied the flights of birds, and then eventually built a flying apparatus like this one, adapting himself or somebody to perform flight. Most of Da Vinci's machinery did not work. Most of his inventions did not work, but practically all of them were inspired by nature. And the fact that they did not work is also contributing to our method in biomimicry or bionics, because not everything that we attempt necessarily has to be successful. Not everything has to work. The experiment itself, even if it proves to be not a success is also quite valuable, and that already points to the important issue that we have and why we use it as a creativity technique in design education. Da Vinci is only the most important representative of such a practice that is based on bio-inspiration, using it as a creativity technique. People have always been inspired by nature, ever since human intelligence first emerged, and up until the 20th century, practically all our inventions and artistic innovations came from the study of nature. Only later, only in the age of science and technology, we adopt a kind of methodology that is in itself sufficient and idiosyncratic. We're no longer making these comparisons, but modern science starts to investigate things under lab conditions, and does so quite successfully, but often the solutions are not lasting. Often the solutions are not the all things considered kind of solutions, and there are side effects and byproducts, and many of the solutions that we arrive with in development, in science, in the industry, well, they solve problems, but they create new ones. And this is also one of the reasons why we start to look at living organisms. Living organisms have evolved and developed in geological time and under evolutionary pressure. So there has been trial and error in the millions. And as a result of this, nature has found the ultimate solution for its products. For example, sharks have been around for as long as the dinosaurs. Dinosaurs, however, were not necessarily a good design, and Mother Nature started to had some other plans for it, finally changed her mind, turned them into birds. But sharks stayed the same. So the evolutionary pressure has pushed the dinosaurs to become birds, but the sharks occupy their niche in the system. So this is a well-adapted solution, and biomimicry is a method that hopes to spy on these solutions, take advantage of it for the things that we create, and even in a larger sense, even in a socio-political sense. The best known example of a biomimicry approach is the invention of Velcro. And you may know this, that Velcro was actually invented based on the observation of this plant, which is a burdock seed. Everybody knows burdock. It's those buds that get stuck to your pants in fall when you take a walk in nature. And the study of this actually fruit is what inspired the invention of Velcro. It was a Swiss engineer by the name of Georges de Mestral who invented Velcro as a fastener in 1941. He used to get those burdock buds on his clothes and in the fur of his dog, and he decided to investigate this, and finally he came up with the idea of a so-called hook and loop fastener, which he patented in 1955. The fastener uses these kinds of hooks like in the burdock plant, but then there is a counterpart, loops. This shows a close-up of a strip of Velcro, and so these hooks hook into these loops, and that became a new type of fastener that fastens on the touch, which is different from buttons or zippers. And the Velcro was the first experiments were done in wire. It's kind of like his bionics gadget, kind of like in my class. And then later on in cotton, all of which did not work very well, a lot of trial and error, but finally in nylon and in polyester. And de Mestral also marketed it. It consists of these two components, a linear fabric strip with tiny hooks, and then there is a mate that attaches it. We can pull apart, and he called it Velcro because this is a combination of the French word velours, meaning fabric, and crochet, meaning hook. And this has become the most prominent, best known example for biomimicry. However, this was done long before we were talking about biomimicry, biomimetics, or bionics in the 1940s. The word biomimetics was the one that was originally used for this method, and it was in the 1950s. The American biophysicist and all-round scientist Otto Schmidt developed this word, biomimetics. Schmidt invented the so-called Schmidt trigger. The Schmidt trigger is based on the study of the nerves of squids, and he replicated this system, the biological system of nerve propagation, to create a kind of like a switch. This is called the Schmidt trigger. And a co-worker, also important for the whole development of biomimicry, a co-worker of Otto Schmidt was Jack Steele, and they worked at an Air Force base in Dayton, Ohio. They were all like aerospace engineers. And Steele coined the term bionics. Bionics was the word that was largely used for what we now call biomimicry, and in continental Europe is still the word that they predominantly use. Steele defines bionics as the science of systems which have some function copied from nature or which represent characteristics of natural systems or their analogs. So there we go again. It has to do with an analog. He sees the transfer of technology between life forms and manufactured objects as desirable because evolutionary pressure forces living organisms to become highly optimized and efficient. And a classical example, almost as important as Velcro, is the so-called Lotus Effect. And you can see the Lotus Effect here. The lotus leaf repels water, and there's practically nothing, no dirt, no paint, nothing that sticks to the lotus leaf. It's self-cleaning. And this has been studied, and scientists, researchers, bionics researchers, have found out that under the microscope, the lotus leaves looks like this. These balls here would be droplets of water. And the nanostructure on the lotus leaf is of that kind here with these bumps. And this creates a dynamic so that the cohesion in the droplet of water is of such kind that the water always pulls away from the leaf. And as it does so, just as every droplet of water wants to form a sphere, and as it does so, it takes with it any particles of dirt or whatever may be on the lotus leaf. And this has been informative to the development of a coating, self-cleaning and water-repellent coating for all sorts of things, for clothes or whatever. This has been replicated. So this would be another very classical example for the development of biomimicry. Now the term bionic, as steel has developed it, took kind of like a funny turn in history because the writer Martin Caden referenced Jack Steele and the term bionic in his novel The Cyborg. And after the Cyborg, there was an American TV series that started in 1971, which was called The $6 Million Man. And because of that, the word bionics now is associated with science fiction. And in the English-speaking countries, the academic communities, scientific communities, don't use that word bionics anymore. However, and they use the word biomimicry. There is a bit of a problem with all the terms, with biomimicry too, because the term biomimicry implies that we're mimicking, meaning imitating nature, which we actually try not to do. And I will explain this as we go along. Now, the term biomimicry was popularized by the scientist and author Janine Benyus. In 1997, Ms. Benyus published this book here, which our library has a few copies of, and which is being read a lot, as you can see. It's called Biomimicry, and it's called Biomimicry, Innovation Inspired by Nature. And she defines biomimicry as a new science that studies nature's model and then initiates or takes inspiration from these designs and processes to solve human problems. Benyus suggests that looking at nature, she suggests that we look at nature as a model, a measure, and a mentor. A model, a measure, and a mentor. Now, you realize this goes a little further. This is not just like making the transfer from nature to technology. There is an overlap here. Biomimicry is not just the science, but it is also one of the arts, because it does not only investigate and generate knowledge, it also creates and produces. It does not only transfer solutions from an organism to an artifact, but it also instigates new products. And product development is a property of the design discipline. Design is an interdisciplinary activity at the crossroads of the arts and science. So at this point, it is really clear that at the core, biomimicry belongs to the design discipline, while originally it seemed to belong mainly to the engineering faculty. Benyus believes that following the example of nature, we will save ourselves and our planet from the ecological catastrophe, and there is a socio-political component. a socio-political element in that. So there are numerous books and public lectures of Ms. Benjes, and she gives examples of many companies who develop products using the biomimicry approach. She is the president of the Biomimicry Institute, which is a non-profit organization and whose mission is to naturalize biomimicry in the culture by promoting the transfer of ideas, designs, and strategies from biology to sustainable human systems design. She's also the co-founder of an organization that is called asknature.org, an online resource that provides examples for nature's ingenious ways of solving problems. Let me see here. Yeah, this is the Biomimicry Institute, the website of Ms. Benjes, an interactive website where you can ask questions and download all sorts of talks and examples for biomimicry, and it's one of the most dominant place for this new discipline. Now, so far we have been talking about research, but it's also at a stage where large companies, practically all multinational companies, all big names, have kind of like a department for biomimicry in their development, in their research facility. A good part of computer engineering, software and hardware engineering tries to take advantage of nervous systems, neurology, various ways. The heavy industry, the car industry, and a very good example for this would be a prototype car that had been introduced. Well, maybe I should show the kingfisher. I'm gonna forward here a little bit. So I hope that I explained this. The whole thing is about a train in Japan, because in Japan they have these bullet trains, super fast trains, which they need for their mass transportation. But when the train goes through a tunnel, as it gets out of the tunnel, there is a bang, which has to do with the speed and the air current and whatever. And this is to be resolved. And for this reason, the researchers had looked at this particular bird, which is the kingfisher, and its peak. So
Earth, sky.
Today, how a kingfisher bird inspired a bullet train. Earth Sky spoke to Sonny Robertson of the San Diego Zoo, which is a center for research and education into what's called biomimicry.
Biomimicry is a way of looking at nature to inspire us, maybe to a way of doing things.
Robertson said that in the late 1990s, Japanese engineers modeled the front of a bullet train after a kingfisher's streamlined, long, narrow beak.
The connection is, in Japan, they have these very fast, what they call bullet trains. They were getting so fast that the typical bullet shape of the face of many of the trains was causing a loud booming sound when these trains would exit the typical train tunnels.
Robertson said the reason the train boomed was that a noisy cushion of air was building up in front of it. It made a boom that disturbed both people and wildlife near the train. She added that one of the engineers on the team trying to solve the problem was a birdwatcher.
So he thought, I wonder if I could apply this principle to the shape of the front of the bullet train.
In other words, the engineers found that making the front of the bullet train pointy, like the beak of a kingfisher, made the train quieter and more aerodynamic. And that's biomimicry, using nature to design sustainable solutions for humanity. Earth Sky is a clear voice for science.
Okay, I think I can close this. It gives you the idea. The train was not only quieter, it also used 15% less electricity, and it travels 10% faster because of this nose that it has, inspired by the kingfisher. And another example for industries using the biomimicry approach is the so-called Boxfish Car, which was developed by Daimler and introduced in 2005 at a car fair in Washington. So they studied this particular fish, the boxfish, which lives in the Caribbean Ocean and has a boxy shape, and despite of its awkward shape, the fish is remarkably hydrodynamic and very lightweight and very robust to shock, and can maneuver in confined spaces better than other fish that look more fish-like. So the engineers and designers at Daimler took inspiration by this fish, and here in this picture it shows how they developed an SUV, a small SUV that can easily transport four people. Yes, and so this is also a very well-known, very good example for how biomimicry is used in the industry, and it is being used a lot these days. But I have to critically say that it is also used as a selling strategy. Green selling also happens, and you can see this any architect will sort of like make reference to a plant whenever it's possible, because whatever is being marketed as green will be a market success. We also have to admit that and deal with that. So this method of bionics or biomimicry in the industry always tries to solve a particular problem, such as the elimination of friction or maneuverability. It isolates that problem first. And then it asks the question, how does nature solve that problem? And it finds an organism in nature that is analogous to that problem. Like the fish would be the analog to the car. Or for example, the skin of a cactus could be analogous to the cladding on a building. And let's say in my building I have to make it waterproof, or I have to make it weather resistant. So I look at nature, maybe at the cactus, maybe at the skin of the cactus. I look at that and see how nature solves that problem. They don't always find a problem. They don't always find the solution. But when they find the solution, they make the transfer from the observed principle to the artifact in order to improve the product. So this linear method, that of course is what the industry uses, and of course this makes sense. But we are using biomimicry as a creativity technique, design education, and we have a slightly different approach, and also we see advantages in this method that go beyond just like improving products. Most design programs In particular, programs in industrial and product design include a course or at least a project in biomimicry. The European schools will do this more intensely than North American schools, and also in Europe they still use the word bionic. As part of the design curriculum, the method also plays an important role in stimulating creativity, out-of-the-box thinking, and critical thinking, and developing resourcefulness. Apart from its value as a method of inventing new products, biomimicry is a very important pedagogical tool, and as I said earlier, we consider it a creativity technique. Bionics is in design education for the designer what is playing chess for strategic thinking. So what chess does for strategic thinking, that's what the bionics method does for creativity in the context of education. And for these reasons, the reason are the projects that we do here at Concordia are not necessarily aimed for the development of a product, but they are predominantly experimental in nature. So we do not start out with a problem. A problem to start out with could be like, how do I efficiently store drinking glasses in a kitchen cabinet without breaking them? That could be a specific problem, but we don't do that. We start out with a sweeping investigation. We choose an object from nature, and we investigate its characteristics, features, and processes, all of them encompassing holistically and in general. But we do work with the analogies, and they are important. We use the analogies from the start, and we compare. We look at an artifact, we look at an organism as if it was an artifact, or an organization, or a managerial system. So we may compare a thing from nature to a building, or a bridge, or a boat, in order to learn of its structural qualities. We treat an organism as if it was a machine, and we probe it for its mechanical, physical, chemical, optical, or any other processes. We may invoke the insight. We may evoke insight as to the social interaction, group behavior, communication, exchange between species, symbiotic relations, and look at the object as if it was a member of society. The octopus is a member of a family. How does it interact with the other octopi? Who eats it and who gets eaten by it? What would happen if we take it out? As if it was a member of society, and the other fish and creatures in the ocean are also member of society. How do they organize their life? How do they interact? Are there symbiotic relationships? And we also investigated how nature composes and designs. How does nature result in beauty, visual beauty? Because most of the principles of composition that we have come from the study of nature. So there are these four categories of research that we use in our assignment. And students have to do in-depth research and dig up as much information as possible. And at this point, they don't know where this will lead them. In their research, they consult primary sources, meaning the object itself, like, let's say, take the fruit, take it apart, investigate it on their own. Then they study secondary sources, that is all sorts of literatures, websites, speaking to experts, and they also do hands-on experimentation. And the research is done partly in a convergent, linear way, meaning systematically, like research is supposed to be done, but this is being combined with a lateral method, with divergent form of research that allows for distraction, that allows to meander, that works with stimulations. And I always say to my students, part of the research that we do in this part of the building would not qualify as research in the other part of the building where the engineers are located. But for us, this is research. In fact, for us, simply drawing this pigeon from observation and memory is already research, because it is an abstraction. When you draw it, you draw from it, you extract from it, you analyze, and you gain an understanding. So all of this research is quite important. And then the researcher, of course, also has to be documented, and hopefully there will be a special discovery. We're hoping to discover something that is special and astounding and motivating, something that has design potential. We don't know yet what that will be. It will be something that could eventually solve a problem, but we don't know yet what is the problem. We kind of finding a solution, and we bank it. We store it away for the rainy day when the problem emerges. And a good part of that whole procedure is play. Play is quite important, and it is being done in a way similar to the kids building a treehouse, driven by curiosity, self-motivated, and for the larger part it works, and sometimes students will even continue with the project after the course is finished. So we're looking for this kind of a special discovery. And to illustrate this a little better, I give you an example. I describe an example. Often it is kind of difficult to photograph the projects because it's not necessarily one project, it's not necessarily always so successful. But I have photos and we'll show you some. Okay, these students studied the wasp, and they discover the wasp has these stripes, black and yellow, and this pattern has a very strong signal effect. It communicates to a potential predator, careful, I'm a wasp, I'll sting you, it'll hurt. Stay away. And we know that, and we know that in our traffic, here in Montreal for sure, a lot, and black and yellow stripes. Very strong signal effect. But that's kind of obvious, right? That's not the only thing. Because the students also find out that the wasp can sting only when it sits still. When the wasp flies through the air, it is defenseless. And the predator always comes from higher up. But the following will happen. The wasp has these transparent wings, which it moves very fast, and this creates an oscillation. And the wasp also flies speedily. And under these conditions, the stripes, black and yellow, will blend. And what kind of a color do you get if you mix black and yellow together? You get some dirty brownish, greenish, grayish, olive non-color. And that is pretty much the color of the environment where the wasp flies through. So the ingenuity of nature is that the same measure works as a signal, as a warning sign, and as a camouflage. And this is one of those astounding discoveries that, and when you get them, then it really gives you the wow reaction. And so now, what can you do with it? How can we make use of that? We should make use of that for our built environment kind of situation in one way or the other. It's not so important that there is a particular use, because we are not producing a product, and it would be presumptuous of us to produce a product. So what we do is we make a demo piece, we make a gadget that proves that this particular discovery has design potential. And then at a later stage, this discovery could be used for something, could be applied. Maybe it can be useful for the military. In this case, the students decided to turn it into some sort of a game, and it was like a disc that they had to throw. And when the disc flies through the air, it kind of blends with the lawn. And when you have it in your hand, it gives a strong signal effect, and the other player can come and grab it from you. And it's an experiment, and at that stage, when we are at that stage, the semester is over, and we have to let it be good. But I had students who actually continued with this, because it really starts a dynamic of personal interest. So these are the kinds of, this is how we approach it at Concordia, really as a creativity technique, and it includes a great deal of experimentation, and also it's quite important that we take risks with this and allow things to eventually also not work. So I don't know if I will probably not have enough time to show you the documentations of the process, but I can show you some examples of students and their projects. So here we have this team. They always do this in teams of 4. This team studied the turtle, and particular interest of them was the neck and how it can go in and out of the shell. Biomechanical situation, which they reproduce in form of this gadget. Biomechanical interpretations or solutions are often conceptually easier, and there are the conceptual part of the project can be quite demanding. Now this one is a structural invention. It is based on the pine cone. The pine cone has these chips, and between the chips are the seeds of the pine, and eventually the pine cone will open up, triggered either by moisture or by heat, and it will then release the seeds. So the students have done all these experiments here, and this is all just paper lined with some other material, and when you wet it, it curls, and when it dries up, it straightens out again. So this is an invention that could be used for some roof or tent or something. And all these experiments, they all worked to a certain degree. So the students would spray it with water, and it'll curl up like this, open up, let the sun in. and then as it dries up, it'll straighten out again. They also experimented with the opposite. When you wet, when it curls up when it dries, and straightens out when you wet it again. And all of this is, well, not 100% finished, kind of like on the experimental side. And you don't even know, sometimes you don't even know, like, is this the finished thing and this the maquette, or is it the other way around? So here we've got another example, and then of course different ideas, different ways of arranging it, different designs, and all of this is done. You have to be resourceful for that. We don't have research labs. We cannot work with, we have to work with what we have, often what we find. And that's a fact of life. So the simpler, the better. Now, another mechanical situation, it is the sting of the scorpion. So it's kind of literal. You could see the tail of the scorpion, and the strings would represent the muscle, and this is how it stings. Now, I have two examples of this, of the same thing here, two different ones. The grasshopper makes this chirping noise. And that's kind of the analogy would be that this being a musical instrument. So how exactly does that work? What are the mechanics? What are the acoustics that go on in the grasshopper between its wings and its thighs? So this part would be the wing part of the grasshopper, and this is on the legs. And well, it explains it pretty well. This is how it rubs the wings against the legs, and then it creates this kind of noise. But another group came up with another solution, and that's this. So the same discovery. The metal piece with the lever would be the wing of the grasshopper, and the wooden part would be the legs of the grasshopper. But this group of students, they included a resonance body, which the grasshopper actually has in its legs. So it's a noise maker. Maybe it's an idea for a musical instrument. We don't know yet. It's a curiosity item. It's a gadget. It's a demo piece. And it's most of all there for us to explore something, to practice inventorship. Okay, these students study the fish and how it propels itself, and what we have here is just a maquette. The fish is structured in this way, which allows for the particular movement that we know from a fish. Now, the fish moves through the water. The water stays in place, the fish moves. Doesn't necessarily have to be that way, because you can also make it so the fish moves, but it transports the water rather than it propels itself. So the interpretation here is that this, being the fish, would wiggle like the fish, and by doing so, the sand, which represents the water, would be transported, brought forward, and fall over the cliff. A conveyor system of some sort. Actually, I think this is all the pictures that I have. I do have some process books, but I think we're short of time, and because people may also want to ask question, maybe I could show one of those process books. The students have to I'm going to show the one with the Venus Flytrap. The students have to document the whole process, all the steps, and they have to make a book. The book will be something that's like between 10 and 20 pages, from the very start, all the research, to the very end. The Venus Flytrap is a very popular subject for our bionics project because it's like a trap. It's actually already suggesting that that there is an artifact. And then when students research this, they will eventually find there are also other things to the Venus Flytrap, but these people actually, this group, they actually worked with the trap idea, in particular with the trigger. And it goes okay. Inside of the trap there are trigger hairs, 4 little trigger hairs, which the insect has to touch. If the insect doesn't touch these trigger hairs, the trap will not close. And then the trap works like, it's like a micro switch. It's like a highly sensitive switch. But the trap has to be charged. There is a convex, there is a tissue that is convex, but at the brink of snapping over into concave, and it achieves its stage through osmosis, through water pressure in the cells. So the cells, it will be like this, but when it's triggered, it'll snap over and it'll close. And this is what the students try to reproduce, because it takes very little of an impact for this snapping to happen. And then the plant cannot do it a second time. It has to recharge. It will take a while. If it does not digest the insect that it catches, if it doesn't catch it, it takes a while until it can open again. And then it still takes a while until it's charged again for the mechanism to be triggered again. So now, how do you reproduce this? So you see there are all sorts of maquettes and experimentations and trials until finally they arrive at a solution like this. So the tension in the material, strip of plastic, makes it stay either convex or concave, and these would be the trigger hairs, and it takes very little for these trigger hairs. It's calibrated so delicately that it easily snaps over to the other side, and in this case they actually made it's a real switch, and it concludes an electrical circuit which is not really necessary for the project. But what's also important is these in-between stages, the experiments. Well, maybe I can show a second one. Let's look at the otter. So they studied the otter, and that's them. Okay. Here they are. And they're lucky. They have access to a biology lab, which is unprecedented. This is because one of them is a double major, and also studies biology. So all sorts of, here they are at the biodome, taking pictures of the otter, studying the primary source, and then all sorts of research and discovery. Main discovery being the fur of the otter, the layers. This is how the computer lab starts to look when these biomimicry students get in. There was some other part of it where it explains the three different layers. The fur of the otter has three different layers, and there is an in-between layer which catches air. Two structural layers provide insulation and water-repelling properties by trapping a layer of air in between them, the real barrier to water and penetration and heat loss. So then they have to experiment with all sorts of tissues and fabrics and materials, which one will perform best, which one can reproduce the fur of the otter effectively. And what kind of structure, what kind of shape do I need for that? And all of this is not something that can be taught, nor can you really find it in a textbook. All of this is done in a trial and error kind of a method and in a play-like method. Like the kids trying to invent a time machine. Like that. With that kind of enthusiasm and fun and entertainment aspect. And finally, we have a concept. Here it is explained what the first layer does and what the second layer and the final layer does. And this is their sketch, their drawing, how to reproduce it. And then they also test it. Test how it behaves under heat. And finally, we have a prototype, which has two sides. The shingles can be flipped over, and then on the underside they are black, and you can use both sides. So one is for heat, and the other one is for cold. One is for water also. So this is how the final project looked like. And here, so the dark side, the dorsal side, and the ventral side, and this would be the back side. I could show you quite a few other of these process books, documentations. They're all kind of fun to look at. But I think you get the idea of this method that we're using for bionics. And it's an important one. And I believe that it sort of puts the student on a track to a self-guided form of study and a more direct and courageous and holistic approach to their study, and hopefully also to their work later on as designers in the industry. And hopefully this kind of an approach will also inform design ethics and the very important issue of sustainability in our field. All right. Well, thank you for attending to me. It's a big subject. Thank you very much.
So if you have questions, please go ahead. So we have time for questions. So
yes.
I thought it was very interesting to see the students engage in primary research and really go to the biodome and look at nature firsthand. But I also wonder if what do you think about maybe have them collaborate with maybe biologists or scientists because they would have a different set of knowledge. Do you ever think about these kind of collaborations?
Yes. That would be ideal. In fact, this last example here was such a collaboration because one of the students, Wednesday, she was a double major. She was also in biology, and this gave them access to labs, and also she brought an enormous expertise to the project. This would be a very good thing, but we have to fit this into a tight curriculum. So the logistics that keep us away from it. Yes.
Hi. Speaking as an architect, have you ever considered the idea, because I've done this with my students before, where they've used the concept of predatory biological organisms, from whether it's a python or it's a hawk, and used their structure and understanding to create something physical that can house a human being. And it's interesting because we have examples such as the Bird's Nest Stadium in China, which is, based on the bird's nest, and for the Olympic Stadium. And it's interesting if there's and I've always been looking into possibilities where students can actually connect with real life professionals who are doing this work, maybe learn from them, because it's one thing to study it in a lab and experiment, which is first-hand learning, which cannot be beaten. It's the best way. But then to take that learning and talk to and kind of connect with an actual professional who's taken it one step further and done something even further from it. It doesn't need to be an architect. Could be, like you said, people in the military who do research, people in the general multinationals of FMCs who do research based on all of this. That could be an interesting kind of collaboration.
Yes. We do this in the second semester.
Okay.
It's really at the start of the design education. And we really use it as a creativity technique. And the way how the students will pursue their projects later on, they will always have this kind of like in the back of their mind. What you suggest, I think this could be done in form of independent studies or maybe even on a master's level. Because if you want to do this kind of a project, you need at least a full semester. Yes.
Thank you.
Yes.
Erwin, you were mentioning before that a lot of, all the research that you guys do with your students is not intended to formulate a final product. is more experimental, and
Yes.
all these become a box, kind of a box of treasures of things that you can use in the future. Do you have any example where some of these has sparked imagination for another step, like a student taking part of this documentation done before by another group in another year, and then continue from there to develop something?
I don't have any examples of the students taking the biomimicry project and then developing it further and marketing it. I do have examples of students continuing with the project after the semester is over. I had one group of students once, they studied the Coral Reef, which is a habitat for all sorts of marine creatures. And their discovery was that, the smaller fish hide from the larger fish. And the even smaller fish hide even further inside of the reef. And everyone is protected. It's sort of like a filtering system almost. And then the students developed an alternative bird feeder, which was installed at the St. James Church right next door. So the thing was really simple. It was a big sheet of plywood, and there were wooden pegs, and in the middle they were very close, and towards the periphery the distance was larger. And then the food for the birds would be thrown on this board. So the tiny little sparrows can go in the center and eat where the pigeons and seagulls cannot go. And the blackbirds will be in the middle, and the larger birds more the outside, so everybody gets something, and the big birds cannot chase away the smaller birds. So that was it. Then the semester was over, and then afterwards they tested it and sent me a video. So it actually worked. The little birds could go in there, but what did not work was the birds had to learn this first. The little birds did not understand that they were protected. And when the pigeons came, the little birds would still have the impulse to escape. So that did not work. And there was one other thing which they had not factored in at all, and that was the squirrels. Squirrels would just climb over it and go everywhere. So, but this is also an anecdote that shows you the project and how it involves students and the entertaining quality that it has. Yes.
Keep on going with the last question. I was wondering if some people were actually working with it. Are you keeping a data bank? Is this something that's available for either other students or for the public to research, and they they have a problem, they're trying to design something and they want to find inspiration? Can they look through the projects to the books?
It's not publicly available, but I have the documentation. I have the process books.
Okay.
Yeah, but it's a half semester project in first year design education.
Yeah, but it could be good for
Yes.
inspiration.
For sure. Yes.
Yeah, that's a similar thing. I was wondering if you know of examples, maybe of when you mentioned, for instance, that every multinational will have in its development and research and design department some biomimicry lab.
Yes.
It would seem that their work would be greatly aided by some sort of which animals do we look at when we're trying to solve these kinds of problems and why, and almost kind of go quicker, right? And if we had
Yes,
do you have
this is what
examples of that
Janine
existing?
Vanius has in her website Ask Nature.
Yeah.
So this Ask Nature website, which you can access through the Biomimicry Institute, you can actually type in a question. So you can type in, how does nature waterproof
Okay.
systems, or how does it communicate? And then it gives you a number of examples.
Yeah.
Yes.
A comment and a question. It surprised me first that it's just the first year that design have this course and doesn't continue over the years, especially for the last year, since it's such an interesting topic and it have not just applications in the sense of learn, but also so many other applications that can be bring to solve problems. Now, my question is, as it happens sometimes in science, when scientists get into learn about art and about the process of art, they get really inspired and they start to do things to the art, and some people even diverge completely to become artists. Do you have students that become interested in science, in scientific applications, or learn more science?
Yes. But most often they will still pursue design studies, but they will then do a minor in a science field, which can also be like computer engineering or software design, or yes.
Great.
There are also some students who switch over, but it's more that they choose a minor or double major. Yes. Yes.
So you made an interesting distinction before about biomimicry kind of being more of a design within the the study of design opposed to the study of engineering, right? So that made me start thinking interestingly about how like a lot of cutting edge technologies that we look at nowadays often taking the shape through biomimicry.
Yes.
There's a lot of the most advanced types of technologies we develop right now focus on replicating processes in nature, right? And so we often see that these cutting edge technologies don't necessarily reach the public application, don't necessarily reach public application initially. And oftentimes they, in fact, become under the possession of the state or governments. And so oftentimes we see the most cutting edge technology start out with the military, for example.
Yes.
The internet being a very good example of that. So what do you think there is to really say about that, the relationship between biomimicry, governments, military application, and these kind of things before they reach consumer products and public access,
Well, there has been a lot that's been developed by the military, and then later on entered the public sector. Kind of difficult for me to answer this question. Not a particular fan of the military.
Right. So that's a huge thing, right? Because oftentimes the best service for these things come when they have access to the public, right?
Yes.
So you have that whole conversation of like the internet being used as a war vehicle of some sort before it reaches this more democratic purpose that it serves, right? So like the application of these things, I think, has a lot to do with this distinction between engineering versus design, STEM versus art,
Mm-hmm.
The human sciences versus the harder sciences like, biology or engineering, right? And what kind of relationship there is to examine there between university students, a military industrial complex, which oftentimes become the first people to possess and gain access to those ideas. Cordura was a military fabric at first, right?
Yes.
Talk about camouflage. That's
Camouflage was invented by an artist, American artist by the name of Thayer, and based on the observation of countershading, entirely for the military. Countershading is a method that nature uses a lot. Well, the object has when the light hits an object, let's say a duck, one side is light lit and the other side is shaded. And because of the shade, it looks round, it looks volumetric. So Thayer discovered that nature countershades. It makes the shaded part darker and the part that is in the light. Now it makes the shaded part lighter and the part that is in the dark, it reverses it. And thereby it flattens it out so the predator does not understand that this is an object, eliminates the figure-ground relation. And this was one of the key inventions for camouflage.
It's making sure that these things get applied for good, right?
Yes.
And for things that benefit society, these cutting-edge technologies get used by things that progress us positively rather than end up as things which.
Well, one thing that I can say to answer this or add to it is it also has to do with the sense of self-responsibility that the designer and engineer will develop. And this self-guided way of working with a holistic approach, well, hopefully this will lead people to take on a responsible position when they develop products. Yes.
So just one comment. The internet didn't start really military. It was a project that was developed by CERN in Switzerland for communication between scientists. It advanced in time through DARPA money from United States for develop the node accessibility in the United States, but it started actually to improve communication among scientists to share information. So
it depends if you're talking about the web or
yeah.
the internet.
Yeah.
I think the internet was the new.
Well, the protocol, the www, is start. Yes, that one start with scientists. The applications after, and even though it was developed further with money from military, the concepts are still scientific concepts, like the fact that the internet cannot be controlled because it's multinodal. And this is one of the things that regulations in the United States today are trying to cut by, control and eliminate the nodality of the internet. So this way you have a control of the information, where it's going or not. Sorry, I just wanted to comment on that. I think we are fair in time. So if you guys want to talk more with Erwin, I recommend you to visit him maybe during the week or learn more of what he's doing in Concordia, especially the Department of Design and Computational Arts that is pretty much focused in sustainability and teaching their students how to make a good and responsible use of materials for the future of design. So I want to just thank you, Erwin, for being here today. Thank you guys for being here. And if you want to learn more about what we are doing, you can visit our website, www.convergenceinitiative.org. We are doing these kind of talks every 1 or 2 months now. So we've been very, very periodic now. So you guys can have more of these fascinating topics of crossovers between science and art and visit the stuff that we are doing. So
and also talk about the videos that are already online.
Yes, that's the other thing. As you are seeing here, I've been recording Erwin. So the talk will be available in a couple of months. It takes a little bit of time for being there, but right now we have at least 10 different talks from people that go from all the way from communications and science to music applications for learn to communicate with people that is in state of coma or things like that. So it's really, really interesting. So just go to our website. You will find a place that's called Sci Art Talks, and Erwin will be there probably in 1 or 2 months. So Thank you so much for coming, and I hope to see you in the next time.